Today we're going to review applications of derivatives, starting with implicit differentiation. I think you'll remember this because you tend to forget that you need that dy dx, and so we've reviewed it quite a bit. But remember that you need implicit differentiation at any point where there are multiple variables in a problem or in an equation, and then you're defining the other variables in terms of a single independent variable. The most common way we see these questions algebraically is in terms of x and y, and we're asked to find dy dx. When I see dy dx, I'm being told that x is my independent variable, and I'm being told to treat y as a function of x. I could, though, have a formula that involved x, y, and z, and then they would have to tell me I'm finding dx dz, or whatever it is. They're telling me what my independent variable is. So I want to find dy dx here. When I go to find the derivative, the 2 is going to come along there, and then when I see y, I remember, oh yeah, y is not the independent variable, so it does have a derivative associated with it, which we can call y prime or dy dx, plus, then the other tricky thing sometimes with implicit differentiation is noticing chain rule. So, noticing product rule. So x times y squared there, well, that's a product because I have x times y squared. So I have to do product rule. Derivative of x is 1 times y squared unchanged, plus x times the derivative of y is 2y, and then times dy dt. I'm treating that y squared as a chain rule question. So I'm doing the derivative of the outside, the 2, the exponent of 2, bringing that down, leaving the inside alone, that's y. Then going back to do the derivative of the inside's y. Don't know its derivative, so I'm going to call it dy dt. And then don't forget to do the derivative on the right side too. The derivative of 2x, since x is my independent variable, is just 2. Then remember the steps to finish solving algebraically. We're looking for dy dx, so we want to take all the terms that don't involve dy dx to a single side of the equation, leaving the terms involving dy dx on one side of the equation. So I think I'll subtract y squared, and I'll have 2, and I'm going to shortcut it now so I don't have to write so much y prime, plus 2xy, y prime, equals 2 minus y squared. Then I can factor out the y prime, and have y prime times 2 plus 2xy equals 2 minus y squared. My brilliant strategy of collecting all the terms with y prime on one side allows me to factor out y prime. Then I can divide. Y prime is 2 minus y squared divided by 2 plus 2xy. If this is a free response question, I'm done here. If it's a multiple choice question, then I may need to look to see, can I reduce it at all? Typically the multiple choice answers are in the simplest form, but I don't see anything I can do with that, so I'm done right there. The next question asks me to write the equation of the tangent line, but I'm not given a starting point, and so there are many equations of many tangent lines, so we'll just move on to curve shape. So I think these rules will be really, really familiar to you. We have talked about them quite a bit, but if they're not, or if you've forgotten, I think that at one point in the year you had a nice lavender colored sheet with all the rules and some graphs on it. You may want to find that, and then make sure that you have completed your notes, your review notes in such a manner that it's helpful for you to review these rules. So the first derivative, we usually use the first derivative to tell us about increasing, decreasing behavior and local maxes and mins of a function. So the first rule that we have, increasing, decreasing behavior of f of x, a function is increasing if the derivative is positive. Thinking about why that would be, just kind of reviewing that graph behavior. If this is my graph of f, remember that the slopes are what the derivative is telling me about. So if I have positive slopes along this portion of the graph, say, or this portion of the graph, positive slopes, then my function is increasing. The same is true in the other portion of the graph that I didn't outline just then. In that portion of the graph, those slopes are negative, and I can see that f of x is decreasing. Local maxes and mins, I usually use the first derivative to talk about local maxes and mins. I see that this function has a local maximum and a local minimum. My local maximum occurs where the slopes are changing from positive to negative. So where my first derivative is changing from positive to negative, I have a local max, or relative max. And then I see where my min is here, that my slopes are changing from negative to positive, and so I have a local minimum. Remember also, and this is very easy to forget, And so this is one of the rules that you probably want to brush up on. There is another option for demonstrating a local maximum or minimum that involves the second derivative. So if I go back and kind of look at these local extrema again on f, I can see that at the local maximum, the graph is concave down. So I may use that information in order to verify that I have a local maximum by saying if the first derivative is 0 and the second derivative is negative, then I have a local maximum. That's not my first choice usually, and almost always if you're being expected to use the second derivative test, you will kind of be forced into it. That is, you won't have enough information about the first derivative to use the first derivative test. Then also I can see there at the minimum here that the graph is concave up. So if the second derivative is positive and the first derivative is 0, then I have a minimum. Just thinking a little bit about process here, these are just the rules, but if I want to use the first derivative test, my process is to find my critical points, so where the zeros are the first derivative, and then use those to do a sign analysis on the first derivative. So kind of remember that process on f prime. I'm doing a sign analysis on the first derivative because I'm using statements about the sign of the first derivative to verify my local max or min. If I needed to use the second derivative, notice that it requires two things. It requires the first derivative to be 0 and the second derivative to be negative. So if I have the second derivative already, that's going to be faster. Sign analysis takes me time. On the other hand, if I don't have the second derivative, it may take me longer to find the second derivative than it does to do the sign analysis. So with the second derivative test, it's much more straightforward, but I do have to verify something about both the first and the second derivative. If I think about knowing where the first derivative is 0, well, I have to know that because this graph has a negative second derivative over much of it, probably about half of the graph I have there. So just knowing the second derivative is negative is not enough. I have to also verify that there's a specific spot where the second derivative is negative and the first derivative is 0. We've been throwing around the term critical points, and we reviewed that when we did the whole year on the board last Thursday. But just as a reminder, critical points, the graph has a critical point where the first derivative is 0 or undefined. Don't forget the undefined portion. Typically with rational functions, we want to set numerator and denominator to 0. And f of x may have a max or min at a critical point, which we've already talked about. And the first derivative tells us about velocity if our function is position. Thinking about the second derivative now, the second derivative is associated primarily in our heads with concavity. And inflection points. Those are the two things we should have associated with the second derivative. The second derivative tells us about concavity of f. It also tells us about the increasing and decreasing behavior of the first derivative because of their relationship. The first to second derivative have the same relationship as f to the first derivative. The concavity of f of x and the increasing behavior of the first derivative are what the second derivative tells us about. So if the second derivative is positive, then that tells us that f of x is concave up, easier to draw it than to write it, and the first derivative is increasing. We have just the opposite information. If the second derivative is negative, then f is concave down, and the first derivative is decreasing. If we are working from a graph, most often that graph is of the first derivative. So we would be using the first derivative statements here, looking for where the first derivative is increasing to say our function was concave up, where the first derivative is decreasing to say our graph is concave up. If we're working in an algebraic setting, we're most often doing sign analysis on the second derivative. Again, if I'm looking for positive or negative, that's the rule I'm trying to use, involves the word positive or negative, I'm doing sign analysis. Then inflection points. Remember that inflection points, when we first define them, they're where the graph of f changes concavity. Since the inflection points involve a change in something, then they involve a change in all three derivatives. So an inflection point is where f changes concavity, where the second derivative changes sign, and where the first derivative changes direction, or changes from increasing and to decreasing. We'll use changes direction familiarly in class. It's easier to say, but if you're writing a justification on the free response exam, you want to use changes from increasing to decreasing or decreasing to increasing, depending on what you're seeing. So make sure that you use the more formal language when you're writing for a test. And we know that the second derivative is acceleration if f of x is position. Again, remember that you must show a sign change. If you're asked about inflection points, or if you're asked about a change in direction, when does the particle change direction? That's a change in the first derivative. When does concavity change, or where's there an inflection point? That's a sign change in the second derivative. So make sure you're thinking about those changes. The second derivative and inflection points actually are associated, and that's not on here, but I think it's on your note sheet, with something increasing or decreasing most rapidly. So remember that as well, that if we have an inflection point where the second derivative is going from positive to negative, then we have an increasing most rapidly situation. An inflection point where the second derivative is going from negative to positive, we have a decreasing most rapidly situation. So make sure that you have that in your note sheet. Let's review a little bit about absolute extrema, since we're talking about extreme values here. Remember that absolute extrema behave differently. Local maxes and mins, there could be lots of those, and so they just occur anywhere the first derivative changes from positive to negative. But if I'm thinking about absolute maxes and mins, there can only be one of those per graph. Only one y value that is a maximum or a minimum. Now, it may occur multiple times, but there can be a single maximum y value. So if I look at this graph, I can see that I would say I have an absolute maximum here and an absolute minimum here. I have other local maxes and mins, but I don't care about those. I want the biggest y and the smallest y. So remember, our key to doing that question algebraically is to make a table of values so that we can easily compare y values. And typically it's x and f of x, although if I was looking for maximum velocity, it would be time and velocity probably. If I were looking for maximum acceleration, I would have x and acceleration and so forth. So I want whatever the function is that's sitting here, that's the function that I want to make the most of or the least of. My x values, what I put on this side of the table, are the endpoints if they're given, and the critical points. And sometimes the endpoints are just common sense, 0 to something, for example. Remember that critical points are where the derivative of whatever this function is, this function sitting on this side, whatever that guy is, that hit the zeros of that derivative are what are going to make my critical points. And then on this side, I just want to evaluate the y values at each of those points. So f of the endpoints and f of the critical points. If I don't have endpoints, then I have to imagine that I'm looking at the entire graph from negative infinity to infinity. So in that case, then I need to think about, well, what happens if I don't have any endpoints? What happens as the x values approach positive or negative infinity? So I either need endpoints if they're given, or I need a statement about the end behavior of my graph. I know that this continues decreasing because, so there's no absolute minimum. Or I know this is the maximum because after this it decreases to forever. So I need to make sure I'm making a statement that indicates to the reader that I've considered all the possible y values, even those that aren't listed because they're somewhere on the end of the graph. Most of the application problems we've seen and done, we have had endpoints given to us, and that makes the question much easier. So just remember that process. Absolute maxes and mins tend to show up more frequently in free response questions than in multiple choice questions. So we'll see those more next week. And then our last little bit of review is related rates. And I'm just going to talk with you about this, and then there are 2 example problems here, and you can work on those if you want. If not, there'll be some in the multiple choice questions that we do in class to remind you of what happens with related rates. So the idea, related rates problems are just an application of implicit differentiation. And that's a situation where we have a bunch of different things varying, all in terms of a single variable. But there's several things varying in the situation. For example, if I start to pour myself a glass of tea, then the liquid in my glass, its radius is changing. My glasses aren't exactly cylindrical. So the radius of the tea in my glass is changing. The height of the tea in my glass is changing. The volume of tea in my glass is changing. All those are changing, and they're all changing in relation to time, how long it's been since I started pouring in the tea into the glass. So that's implicit differentiation over a whole bunch of variables. Time is my independent variable. Everything else is varying in accordance with time. That's a pretty easy example to imagine, and I think the common ones you'll recognize, the Pythagorean theorem ones, the ones with the ladder sliding down the wall, those are the kinds of things that you're likely to see in multiple choice. Free response can be trickier, so pay really close attention when you start a free response question from a formula, that you are thinking about what the variables in that formula are representing, so that if they change variables somewhere along the way, then you're alert to the fact, oh wait, they've introduced a new variable. So I think we did a problem in class earlier, I don't know if you remember it, but the initial formula was giving us the temperature that it felt as a function of wind chill. Take that back, maybe the wind chill as a function of wind velocity, that's what it was. So the temperature that it feels like wind chill as a function of wind velocity. So my two variables there were effective temperature, so wind chill, and velocity of the wind. Then somewhere towards the bottom of the problem, they introduced time as a variable. Maybe it got colder an hour since midnight or something. Okay, well now I have a new independent variable, which means no longer are wind chill and no longer is wind chill a function of wind velocity. Now both the wind chill and the wind velocity are functions of time. So make sure that when you read, be really alert to the wording with respect to or in terms of, because a lot of times they're introducing then a new variable, the question writers are, and you should be alert for related rates problems in those situations. And we'll do some free response questions that are like that, but not until next week. So that's it for today, and tomorrow we'll be reviewing in class applications of derivatives. See you then.